All right, well, welcome to Wave Club, everybody. My name is Josh Jacobs. I'm one of the organizers of Wave Club, our online meeting group to talk about traveling waves in the brain and all things related. My co-organizers of Wave Club are here on the screen. That's Bard Ermentrout, Uma Mohan, and Irfan Zabet. Our speaker today is something I'm really excited about, Andrea Alamia from CNRS in France, giving a talk titled The Predictive Coding Perspective on Oscillatory Traveling Waves. And I just wanted to give a couple of, so the main event, of course, is that Andrea is going to give a talk and we'll have an interactive Q&A session afterwards. I just want to give a couple of guidelines about how things work for Wave Club, for those of you who haven't seen. You can check out, one of the best features of this is that all of our Wave Club sessions are recorded and saved on YouTube. You can access them from going to youtube.com/@waveclubseminar. Uma and Irfan have done a nice job archiving it and editing out the silly things that I say in the beginning and stuff like that. So if you want to review some of the information that you saw, or if your colleagues are curious about the kinds of information, like the presentations that happen at Wave Club, you can check it out here. And also, we are trying to disseminate information about upcoming Wave Club events. We run these roughly every month, usually the first Tuesday of every month at noon Eastern time. And we're now mostly on Blue Sky instead of Twitter, although I think we're sharing information on both Twitter and Blue Sky about what the upcoming sessions are. So you can follow us at Wave Club Seminar is our handle on Blue Sky, and here's a link which you can type in also. You should be able to search and find it. It's a new time for social media. The plan for the presentation is roughly that each speaker, including Andrea today, will give a 40-minute talk, leaving about 20 minutes for questions. It works really well to use the Q&A feature for questions, and because that lets us kind of organize things thematically. And what we'd like to do is, because this is a relatively small group, and because people aren't really Zoom bombing anymore, just kind of bring the speakers on stage. Let us know if you don't want to be on stage, to have a conversation with our speaker, because that's more informative and fun. And we are always looking for new speakers for Wave Club. The theme in general is to cover topics related to traveling waves, but we're trying to have a broad scope of that. Human work, animal work, theoretical work, empirical work, scalp EEG, MRI, invasive recordings, all kinds of things. So feel free to suggest speakers to us and or to self-nominate speakers. That's great also. So our speaker today is Andrea Alamia from CNRS in France. Andrea has a PhD from the Catholic de Louvain in Belgium. He did a postdoc with Rufen van Ruelen and also at Brown University. And he's done quite a broad range of work, not only traveling waves and predictive coding, which is what he's going to talk about today, but he's also done work on deep learning as well at Brown. I'm going to stop right there and let Andrea take it away and tell you about his talk. So if you have questions, please use the Q&A feature. Andrea, you can go ahead and share your screen. Bard, Irfan, and Uma, did I miss any details? Okay. Good. All right, great. Well, thanks everyone for coming, and I'm really looking forward to your talk, Andrea. So thanks for coming here. I appreciate it.
You're muted. Unmute yourself. Oh, Uma, can you unmute him?
Nice. Thank you very much. Yes, I couldn't do it. So thank you so much to the organizer for inviting me. I'm very, very happy and excited to join the Waves Club. I've been following through YouTube and when I couldn't attend, it's really great. Thank you so much. So as mentioned, today I'm going to talk about the link between predictive coding and traveling wave, which is the main topic I've been working on in the last few years. And so this is basically what's on the menu today. I will start from the very beginning. So some work we did with Rufen van Ruelen during my postdoc to the first link, let's say, computational link between traveling wave and predictive coding. And then I will dive more into experimental data, mostly actually only EEG data, so surface EEG data, on things that we did and things that it's actually ongoing. So I will present briefly three studies that try to tackle this question more directly. And eventually, I will finish on some methodological considerations that are particularly important, I think, for EEG in the interpretation of the EEG analysis for traveling wave. So it's a bit of a lot of things, a bit of an overview of all the work we did. I will try to cover as much as possible without entering too much into the details of all these studies, but don't hesitate, of course, during the questions if something is particularly interesting or you want to go deeper into the details. So let me start from the very beginning. Let me remind you in a nutshell about predictive coding. And the idea is that in predictive coding postulates basically that sensory systems are generative hierarchical processes where a higher region predicts the activity of lower region, and the difference between the prediction and the actual activity, so for example, the input, is the prediction error, which is used to update the next prediction. So in other words, we can imagine that the brain has a model of the world that keeps generating prediction about the environment, and this allows us to efficiently interact with our surroundings. Okay, so basically that's what we did with Rufan back in 5 years ago now. We implement the simplest model of predictive coding. So there are two levels. The higher level generates prediction, YDT, and the difference between the prediction and the actual activity, which is the input, is the prediction error, XDT, which is used to update the prediction. So this is the simplest minimal implementation of predictive coding, but it's actually quite boring because it's not doing much, right? The prediction will be corrected immediately, and so eventually the prediction will be exactly as the input. So to spice things up a little bit, we introduce biological constraints. So now we take some time, delta t, for the information to travel between brain regions. And we also add some temporal time constant, basically. So it's the same equation, just with temporal delays and time constants, so some biological constraints embedded in the model. And if we do this, if we include these constraints, then what we observe that our model, if we consider, for example, that the prediction YDT is our proxy for the EEG, and if we compute the response function of the system, what we see is that this response function, this IRF, is actually oscillating in the alpha band with these two values, tau 17 milliseconds and delta t 12 milliseconds. So basically, the very first take-home message of this very, very simple model is that predictive coding with some biological constraint, especially the temporal delays, give rise to oscillatory dynamics. And then we see, okay, well, tau equals 17 milliseconds, delta t 12, we got alpha. Can we see whether there is a link between this parameter and the frequency and amplitude of the oscillations? And so we basically test more methodically somehow the frequency and the amplitude of our oscillations. So on the x-axis, we have the temporal delays, delta t. On the y-axis, the tau. And the color code are the frequencies. So in red, you can see alpha band, which emerge for values that are biologically plausible. Let's say that dozens of milliseconds, 15 milliseconds is approximately the time that it takes for the information to travel between, say, V1 and V2, for example. And another interesting thing is that if we shorten this delay, so if the temporal delta t becomes shorter, so faster or more local dynamics, then the frequency also gets faster. So we enter into the beta range, which is, again, kind of an interesting emergent property of this very simple model. So first take-home message, very simple model of predictive coding with temporal delay give rise to oscillations. So we say, okay, two layers, why not make it a bit deeper? So we went to n layers, whatever the number of layers. And the question look a bit scarier, but it's exactly the same thing. So we have a prediction error, xdt, which is the difference between the prediction and the actual activity between layers, L. And this prediction error is used to update basically the prediction. We also included a prior. So now there is at the very end of at the highest, let's say, level of the hierarchy, there is some endogenous activity that keeps generating prediction about the environment. So in this very, very simple model, the input was white noise. And so also the prior is white noise, predicting basically the environment. So we have a very simple predictive coding model with the prediction error updating the predictions and input on the one end and prior, let's say, on the other. So now if we look at the dynamics of this model, so if we see how the prediction evolves over time, we see that if we feed the model with some input, so if we give the model some white noise during the input, then this input, this stimuli generate oscillation. So let me tell you first of all what is on the image. So on the x-axis, there is time. On the y-axis, there are the layers. So in this case, the model was composed by 7 levels. And the color represent the activity. So yellow and blue are the peak and the trough of the oscillations. So you can see, first of all, that each layer is oscillating. So you have alternation of peak and trough. But what is more interesting is that this oscillation is actually propagating as a traveling wave. So when we feed the model with some input, some sensory or some visual input, let's say, this generates an oscillation that starts at the very beginning, let's say, of the model, occipitally, so to say, if we can already make a parallel with the brain, and then propagates all the way up to a higher region. On the other hand, if we kill the input, if we keep only the prior, then this prior takes over this activity and propagates top-down or bottom-up. So the very simple prediction of the model somehow is that there is this oscillation generated by predictive coding mechanism that propagate forward or backward depending on the cognitive state of the system. So whether we feed the model with an input or not. So oh yes, I'd like to mention before going into the experimental data that there is also some ongoing, actually not ongoing, but some work done by Jakob Schwenk, who is a great postdoc, an excellent postdoc in the lab, who actually took this very simple model and make it much more biologically plausible. So what we did with Rufan was fairly simple. What Jakob did is basically taking the same idea and bring it to the next level biologically. So each region now is composed by several laminae. And he basically implemented an architecture which is grounded on what we know about the connectivity of the lamina. And he basically identified two pathways for the backward and forward wave. One is the infragranular pathway, let's say, related to the forward waves, whereas the predictive coding one that I just described is basically embedded in this blue loop in different cortical columns. So I won't enter into detail just for sake of time, but if you're interested, we just upload on bioRxiv the preprint. So please feel free to dive in. It's very interesting. And it's the same idea, more biologically plausible somehow. So back to our data. So we have our prediction from the model. We have forward and backward wave, depending on whether there is an input or not. Can we test this prediction in our data? So we took our EEG data and we see how can we quantify this traveling wave? How can we see the waves? So we basically take the midline electrodes from OZ all the way up to FZ. These are our 7 regions as in our model. And we create the 2D maps as we did before. So on the x-axis, there is time. On the y-axis, there are the electrodes. And again, the colors represent the amplitude. So yellow are the peak and blue are the trough of our oscillation. And you can see already here, just with naked eyes, that there is a constant phase shift of this oscillation. It's actually propagating occipitally all the way up to frontal regions. So these are schematic data just to ground once again the difference between forward and backward wave to make sure we are all on the same page. So imagine you have 7 electrodes, occipital E7, E6, and frontal all the way up to E1, E2, for example. You have some pink noise, whatever, some background activity, and then an oscillation starts, rise occipitally, and propagates all the way up to frontal region. So this is a forward wave going bottom up from occipital to frontal, or vice versa. The oscillation could start very frontally and propagates all the way down to occipital region. So this is a backward wave. So this is basically how we think of traveling wave in a very simple wave. So we just focus on this midline of the electrodes for the moment, and we see wave propagating either forward or backward. But how do we actually quantify, right? So we can create these 2D maps, okay, very nice, but how can we actually extract some values? So to do this, let me remind you in a nutshell about the 2D FFT. How does it work? So imagine that you have a maps like this. So again, on the x-axis time, on the y-axis electrodes, and now we have an oscillation that is basically traveling top-down from the upper part, from the upper part to the lower part, like in this case. And if you do a 2D FFT, if you move to the spectral domain from here, then what you get is 2 peaks on this axis. On the other hand, if you have an oscillation which is traveling left to right, like in this case, then the peaks now will be on this other axis. And of course, the distance from 0 depends on the frequency of the oscillation. So here it's faster, so they are farther from 0. Okay, now if we rotate, let's say, clockwise or counterclockwise our oscillations, then also the spectrum moves. And that's interesting because these 2 patterns are exactly what we are looking for, right? This looks very much like our backward traveling wave, starting from the upper part and propagating down. And this looks like our forward traveling wave, propagating the other way around. So basically, what we can say from this intuitively, that to get the idea of the 2D FFT, is that this upper quadrant give us basically as a function of the frequency, the amount of power of the wave propagating forward, whereas this quadrant, the lower one, which is the same as this one, tells us how much power there is in the wave propagating backward. So it's a very simple, computationally very cheap way to have a measure, let's say, of our traveling wave. So how do we actually apply it on our EEG data? So we have our EEG over time. our midline electrode, OZ to FCZ. So this is actual EEG data. We extract our 2D maps. So again, time on the x-axis, electrode, and the color are our amplitude. We compute the 2D FFT, and we extract the forward wave from this quadrant and the backward wave from the lower quadrant. We can focus on a specific band, like alpha, or we can take the whole spectrum. So that's nice, but we are not done yet. We still need a baseline to compare our results with a null distribution. So what we did in most of the studies, we take our 2D maps, we shuffle the order of the electrodes several times, and this creates our null distribution, our surrogate distribution. So we have basically destroyed the spatial information, and we only kept the temporal one. So we still had our 1 over f with a little bump in alpha, for example, but we have now messed up, we have destroyed the spatial component, the phase organization of our signal. So now if we compute the 2D FFT of these shuffled maps, we get our forward and backward waves, surrogates wave, which is our baseline. So all the results that you will see from now on, they are expressed in decibels. So it's basically a ratio between the real data, so the order electrode, our forward wave, compared to our surrogate distribution. So if it is close to 0, it means that there are no difference whether I shuffle my electrodes or not. Whether it's higher or bigger than 0, then there are more wave than chance, where chance is our shuffling. So all the data now on are expressed in decibel. Okay, so back to our model. We had our nice model, and we was making predictions. So if we have an input, if we see an input to the, if we feed the model with an input, then we should see forward alpha wave. If we don't have our input, then we should see backward wave. So now we have the tools to test this experimentally. We can run an experiment and compute our traveling wave to see whether we can see this forward and backward. And that's what So Yang Pang did. She was a PhD student in the lab with Rufan, so still during my postdoc here somehow. And what she did, she basically ran an experiment in which she compared 5 seconds of visual stimulation, where there was either a big disk was flickering for 5 seconds, or a very boring white patch that was staying there for 5 seconds. We don't care too much here about the difference. We're just 2 different stimulation. So 5 seconds of visual stimulation and 5 seconds of blank screen, so quite screen. And she computed a traveling wave during these 5 seconds and compared the results. So here what we found, on the left side, there is the dynamic condition, the flickering one. On the right one, the static condition, so the boring white disk. The shaded area are the 5 seconds when there is visual stimulation, and the white one is the rest period, so when there is no visual stimulation. The red is the backward wave, and the blue the forward wave. So you can see that when there is no visual stimulation, so the white area, there are no forward wave. Our forward waves are around 0 in decibel, but there are a lot of backward wave, as predicted somehow by the model. Whereas during visual stimulation, there is an alternation of the two. So there are both forward and backward wave alternating over time in both the dynamic and the static conditions. So this is very much in line with the prediction of our model, which was saying, okay, when there is no visual stimulation, then you should see mostly backward waves. Whereas when there is visual stimulation, then you see both forward and backward waves alternating over time. Okay, so we could match somehow the prediction of our model, but then we want to go a bit farther, right? So the whole idea is to ground our traveling wave to predictive coding. So the idea is, okay, these top-down waves are actually carrying prediction, and these bottom-up waves are actually carrying sensor information or prediction error if we fully commit to the predictive coding. And so if we embrace, let's say, this hypothesis, we can push it a bit farther and formulate more precise hypotheses. In particular, I like to take the example of driving a car. Let's say we are driving a car and we are in Toulouse. Here it's very sunny. And so you see very clearly how far is the car in front of you. For example, 3 meters plus minus 10 centimeters. So in this case, we would be in this condition on the right. So we have a nice estimates of how far is the car in front of us. So we have as more variance, so high precision of our estimates. And if we are in this case, then we should see, ideally, more top-down waves, because we know exactly what's happening. We can predict exactly what's happening in the environment, and very little prediction error, because everything is clear. On the other end, if you are driving in Glasgow, and it's rainy, foggy, and maybe we had a few whiskey because it's Scotland, so why not? Then basically now the car in front of us could be 3 meters plus minus 2 meters. So we are not quite sure where the car is. And so in this condition, we have less precision, so less top-down waves, and more bottom-up waves. So we are sampling the environment more quickly, more frequently, let's say, to update our representation of the world. So of course, this is an anecdotal example, but just to give you the idea of this prediction, this hypothesis that we could test experimentally, whether we can manipulate our prior and see whether this influence our traveling wave. And that's what we did first very indirectly. So I will show two studies in which we went in these two extreme conditions, but relatively indirectly, but I think it's still quite interesting. So the first one is a collaboration with Robin Carr-Harris and Christopher Timmerman, who back in the days were both in London in the Psychedelic Institute. So they study how psychedelics influence the brain activity. And Robin and Carl Friston, they have this hypothesis, this idea that psychedelics, what they do, they basically relax the precision of high-level prior of belief, thereby liberating bottom-up information flow, which is pretty much what we describe here. So according to their hypothesis, when you take psychedelics, then you are basically messing up your model of the world. And if that's the case, then we should see indeed an increase of prediction error of forward waves and a decrease of top-down waves. So we got in touch with them, they contact us, and they were very kind to share their EEG data, in which they basically give to the participants in the first session placebo, so nothing, basically placebo, and in the second session DMT, which is a serotonergic drug, which is a very powerful psychedelic drug, which is used in some shamanic ritual, for example. It's in the ayahuasca brew, so it's altered quite a lot the state of consciousness, and it generates a lot of visual hallucination. And so the idea was to see, okay, once they inject this DMT to the participant while recording the EEG, do we see an increase of forward traveling wave? And that's what we found. So on the x-axis, you have pre and post injection for the forward wave in blue in the upper part and the backward wave in the lower part. The dashed line is the placebo. So the first session, they came, they did nothing. They were sitting very comfortably with eyes closed during both sessions. That's important. Eyes were closed. So during the placebo, there were no forward wave and there were backward wave, which is basically replicating the results of Cao Yang. So that's very reassuring. That's very nice. What is interesting is that the second session, as soon as they get DMT, there is an increase of forward wave and a decrease of backward wave, very much as predicted somehow by our model. And you can appreciate the time course on the right panel. So it's in minutes. So it increases right away as soon as there is the injection, and then it decreases the forward wave over the 20 minutes. Of course, it's dose dependent. So this is very much in line with the prediction somehow of our model. Of course, it's an interpretation. I'm very well aware that it's indirect evidence, but it's still interesting that it's going in the good direction somehow. Okay, now can we test this on the other side? So can we go in the other side of our spectra, let's say? And this was a collaboration with Dario Gordillo and Michael Herzog in Lausanne, in Switzerland. And there is this hypothesis that basically suggests that in schizophrenia, there is the schizophrenia patient, they actually have more precise high-level prior. So basically in this, we are in this condition. So high-level prior, they are much more precise, they have stronger belief about the world. And if that's the case, well, then during rest or during our recording of EEG traveling wave, we should see more top-down wave and less bottom-up waves, opposite to the DMT study, basically. So it's actually important to be a bit more precise. I will clarify a bit better how it is theorized, which again is an hypothesis which is very much debated in the literature. So it's again, kind of indirect evidence, and it's still under investigation whether this is the case or not. But what has been proposed by Sterzer, Corlett, and Adams, and a few others, is that indeed high-level prior in schizophrenia are much sharper, much more precise, so they have a clear representation of the world at high level, but low sensory, lower prior, so sensory prior, they're actually looser. And the fact that the higher level prior are more precise is a consequence of the fact that the low level prior are actually looser, but I won't enter into the details. But it's important to keep in mind that in schizophrenia, according to this framework, we should see more top-down waves during rest, for example, and more forward waves, like in the DMT case, during a visual task. So with Michael Herzog and Dario Gordillo, they share a very nice data set with a lot of patient and control who did both rest and a visual data set. So here I'm showing the rest data. On the x-axis, you see the spectrum for the traveling wave forward, the upper part in blue, backward in the lower part. The solid line is the control, so the healthy control, and the dashed line is the patient. And on the right, I basically average for frequency band. So the usual theta, alpha, beta, low and high beta, and gamma. And we care mostly about, actually specifically about alpha, because that's where we have our hypothesis. And indeed, as we kind of hypothesized, there is an increase of backward waves, in the patient. So in schizophrenia, you have stronger top-down waves during rest and less bottom-up waves, in line with what was predicted by the hypothesis. Now, they also had the same patient did the vernal visual task. So it's a visual task. We don't care too much about the detail. They just have to judge whether the two lines were more aligned on the right or on the left. Kind of detail with different condition. We don't care much about the details. What we care about is that the subject, the participants, were actually doing a visual task. And during this visual task, what we observe, again, on the upper part, there are forward waves. On the lower part, backward waves. We focus on alpha, so the second column. Again, each column is a frequency band, but we just don't care. We focus on alpha. And we see that at 0, so at the onset of the visual stimulation, there is an increase of forward wave in the patient group as compared to the control, which again is as predicted by the model on the other side. So there is less loser prior, so more sensory information that goes through in the schizophrenia patient. And this is specific to alpha, so we don't see this pattern in any other frequency band. Okay, so this is kind of interesting, kind of cool, because we have these two very indirect. I'm very well aware that is very indirect evidence for this link between traveling wave and predictive coding, because both in the DMT case and in schizophrenia, there is a very strong hypothesis that DMT is modulating the prior, the same in schizophrenia. So it's all very indirect. I'm super aware of this, but it's kind of going in the good direction. So that's very interesting and promising. So what I'm going to present now, it's basically 3 studies. I will go fairly quickly, in which we try to test this hypothesis more directly. So the first one is the work that is being doing currently by Martina Pasqualetti, who is a PhD student in the lab. And what we thought is, okay, let's see whether we can test traveling wave during a statistical learning task. So basically, participants were looking at the fixation cross, which were actually below the figure. So here, just for representation. They were looking at the fixation cross, and every second, the shape was changed. So there were 4 shapes that were changing regularly every second. And at the beginning of the trial, each trial consisted of 18 shapes. At the beginning, they saw a shape, let's say a triangle, and they had to press as fast as possible as soon as they see the triangle. So it was just a detection task where these shapes were changing every second. And we measured the reaction time, the pupil size, I will not talk about it, and the EEG, so the traveling wave. What is important, of course, it's a statistical learning paradigm. So the way the shapes were changing were not random. I mean, not always random. And so we actually manipulate the transition of the probability transition between shapes. So these are the tables. I think it's a bit clearer with this representation. So in one condition on the left, for example, the square 90% of the time we're becoming the diamond. So very predictably, okay, if I have a square now, then next is gonna appear a diamond. And rarely, only 5% of the time, either a circle or a triangle. So in this condition, there were very high predictability. On the other end, and we basically play with this probability. So it's 90% or 80% or 60% or very random. So in the 33% case, it was absolutely unpredictable. And we have a condition which was a bit funnier, in which was half predictable, but still with a rare event. So basically, we manipulate the transition probability of these shapes over time. And we have 2 specific hypotheses. The first one is that in theory, if these statistical regularities are manipulating the prior, then, well, we should see more backward waves in the predictable condition and more bottom-up and less backward wave or more bottom-up waves in the random condition. So in theory, this regularity should manipulate our traveling wave, backward traveling wave. And the second hypothesis is that in the predictable case, for example, but actually in most of them, there is a rare event, right? So if I see a square and I learn the statistics, then I'm expecting a diamond. If I see a circle or a triangle, then there is a prediction error because this is a rare event. And so in this case, I should see an increase of forward wave specifically to the rare event. So when there is a prediction error, a rare event, there should be an increase of forward wave. So we have these 2 hypotheses. And the other thing that Martina did, which was actually very smart, was to categorize the participants into groups. So the first, based on the learning index, so basically whether they use or learn the statistics over time. So we basically compare the reaction time when the shape were expected against when the shape was rare. So if they are using the statistics, if they learn, they should be much slower in the rare case because they were not expecting this. So it's a target, but I was not expecting, so it would be slower. And so the learning index would be higher. So we basically apply a median split to categorize the participant for each condition into groups. The one that use the rules and those who don't use the rules. So I will go quite quickly on the hypothesis. I will start from the behavioral results. We have 30 participants. I forgot to mention that at the end of each block, we ask them to rate how much was predictable the sequence. So it was not implicit, it was very explicit. They were aware that there were some regularities. At the end of each block, in which the regularity was constant, we ask them, okay, how much would you be able to predict? How confident you are about this predictability? And all of them, there is a trend over condition. So all of them, all the participants rate, let's say, consciously this condition. And of course, those who use more the rule, so the one that is labeled here as more, sorry, they judge them as more, and they were even more confident. So there is a difference. Of course, nothing surprising here. And also about the reaction time, there is nothing surprising. So the more was predictable the target, the more was predictable, the more expected, the faster are the participants. All of them even more when they actually use the task. Okay, so behaviorally there are no surprises. All makes sense. They use the rules, and some groups of subjects use them more. So there is a difference between the two groups. Okay, what about our traveling wave? Well, the first thing which is interesting is here you see the backward wave on the left and the forward waves on the right. Each color is a condition, the different condition in which we play with the probabilities. 0 is the onset of the stimulus. -1, of course, is also the other onset, is regularly every second. What we observe is, first of all, there is a modulation of the wave based on this irregularity. So there is an increase of backward wave just before the onset of the stimulus, and there is an increase of forward wave after the onset of the stimulus, like related to sensory processing, which is already interesting. We are digging more in this direction, but there was no difference between condition in the backward waves. So here, what Martina did is test the first hypothesis. She checked basically, these are backward and forward waves as a function of the different condition on the x-axis for the two groups. And basically, there is no difference between the conditions. So backward waves, they don't care at all about these statistical regularities. Whether it's predictable, whether it's random, backward waves, they are doing their job. And this is very reliable. So the bias factor was actually providing evidence against the alternative hypothesis. So, okay, looks like our first hypothesis doesn't really work. Backward waves in this specific design, so where everything is clear, sensors, so the shapes are very nicely clear defined. Backward waves, they couldn't care less. Okay, what about the second hypothesis? Here we found something interesting because, so what we see here is for the two group, on the left, there is the group of participants who learn more or who use the statistics more. On the right, there is the group that use them less. And in red is the forward wave in response to the rare event, in blue to the expected event for all the condition. And we can see that in both groups, there is a difference between the rare and the expected, the rare and the expected condition. And we can see this even better if we do the difference between them. So if we do the difference between rare and expected for the two groups, we see that all of them are above 0. So both groups have more forward wave after a rare event. And this is also as a function of the condition. So this effect is higher, more predictable is the condition. We also, I didn't put it here, but we also correlate, we thought at first that this could be related to arousal. So there is an event, a rare event, they are more aroused, and so there is not a prediction error, but just generally aroused, but this effect does not correlate with the pupillary response. So we kind of maybe think that could be something more than just arousal, but we are still kind of digging a bit in this direction. Okay, so this is the first experiment that Martina is doing. We are finalizing working on this. So testing this link between traveling wave and predictive coding via statistical learning design. I want to mention very quickly another experiment, which I find it very funny. This is a collaboration with Matthew, Nassar, and Brown. And it's very nice because he published a paper some years ago with a very cool task that I found very amusing. There is basically a cannon who is shooting ball on this circle, and your task is to basically shield to intercept this ball. So you place the center of your shield, then you see the ball, where the ball landed of the cannon, and then you see whether you intercept it or not. So the size of the length of the shield changes every trial. And the idea is that here you can see where the balls land, but you don't know whether you are successful or not. And in the second part here, you know whether you are successful or not. So to disentangle basically the reward part with the updating of the model. Why the updating of the model? Because the cannon shoots with some regularity. So in one case, the cannon keeps shooting in one direction, let's say vertically, and sometimes, very rarely, it shoots somewhere else. But the participant is instructed that this is an oddball case. So the balls that lands in another direction, they have to be ignored because the cannon will keep shooting in one direction. So you can see it here. On the y-axis, there is the degree. There is mostly shooting around 200-300 degrees, and sometimes you have an oddball. Okay. On the other end, in another condition, so in other blocks, you have the change point condition. So when the cannon is shooting in one direction, then at some point it changes, but then it keeps changing. So now in this case, you have to update your model. So the cannon is shooting, then it starts shooting in the opposite direction, and then you have to say, oh, okay, I have to update, and now I need to put the shield in another position, and then again, and then again. So in one case, it's exactly the same task, but in some cases, you have to ignore the oddball. In other case, you have to update your representation of where the cannon is shooting. And this is very cool because this is very much the essence of predictive coding to some extent. And so I contacted Matthew and I told him, okay, can we actually share the EG data publicly available? And okay, can we see whether the traveling wave, if there is a difference between the oddball and the change point condition? And what we found is all very, very preliminary. We just start to touch the data a bit, but I found it very cool, so I like to share it. We have on the upper part, the forward, the lower, the backward. On the left, the oddball condition. So the solid line is the oddball. So if I go back here, are basically all these little guys. And the dash line are all the others. And there is no difference between the two of them in neither the forward or the backward, which makes sense because you have to ignore the oddball, so that's okay. But in the change point, what is very interesting is that there is an increase of forward alpha waves after the change point and not in the other condition. So when you have to update the representation of where the cannon is shooting, then there is an update of the model. So there is a forward pass of prediction error, let's say, that is updating the model and say, okay, guys, now you need to update your representation. The cannon is changing the direction. And that's very cool. I mean, it seems solid. We are still digging to make sure that it's actually there. There are no confounds, but it seems to be interesting and correlates with the amount of the prediction error. And here I'm just comparing the oddball case and the change point case, so different trials. So this is all very preliminary, but it's kind of going in the good direction to see that maybe if these forward waves are somehow related to model update. And then the very last experiment I want to share before having wrapping up with a methodological consideration is some work that I did in yet another collaboration with Luca Tarasi and Vincenzo Romei in Italy. And they also have a very cool task in which basically participant is asked to keep fixation. So keep fixation at the center of the screen. Then there is a queue, a probabilistic queue that is basically telling you, okay, the probability of observing a target or not. So if it's very high, like 90% of the time there will be a target, very low, 20 or 30% of the time there will be a target. Then after an interstimulus interval, there would be a grid, and embedded in the grid, there could be the target or not. And so the participants, they are just basically, it's a target detection task, very boring target detection task, with the stimuli lateralized on one side, and a probabilistic cues that help you doing the task. They split the participant in two groups based on how much they use this cue, based on the criterion, basically. And they label them believers and empiricists. So the believers are the ones that actually rely on the cue. So, okay, if you tell me high probability, then I'm going to use this information. Whereas the empiricists, they use less the cue and they rely more on sensory data. And they compute traveling wave along several lines of electrodes. So not the midline, but now on contro and ipsilaterally. And this makes sense because the stimulus is lateralized. So we expect to see more traveling wave, forward wave, for example, contralaterally to the attended location. All right, so what they found is, so on the upper part, there are forward waves. The solid line are the empiricists, the dashed line are the believers. So empiricists are the ones that actually look at the stimuli more, let's say. The believer are the one that relies more on the cues. And the first interesting thing is that regarding the forward wave, on the x-axis, there are the different lines of electrodes. And what they see is that there are more forward waves in the empiricist group than in the believer group, which is kind of nice. Maybe because they are sampling more, they rely more on the sensor information, so they have a higher amount of forward waves. That could be a possible interpretation. But what is more interesting is that the backward wave, they are actually lateralized according to this distinction between empiricist and believer. So the believer, which again are the one that use more the cue, they have more backward wave contralaterally to the cue. So it's as if there are more prediction going on in the attended location. But this is not modulated by the cue. But still, it's as if they're using the cue no matter what, right? So whether it's predicting or not in either direction, then they're still using more this information. And what is also interesting is that there is a correlation in the backward wave between the amount of waves and how much each subject used the criterion. So the more they have backward wave, the more they are believers. So the stronger the criterion, the more the bias in the prior. All right, so this is all the experimental data I wanted to show, and I know it's a lot of data all at once. I hope that more or less made sense with this topic about predictive coding and traveling wave. I would like to show one last thing, which is a bit different. It's very short. It's a methodological consideration about EEG and traveling wave, but more broadly traveling wave. And this is work that we have been doing with Martin Vink in Frankfurt, Frédéric Chavan in Marseille, and Antoine Grimaldi, who is a postdoc here in the lab. And we are thinking about this difference in the traveling wave. So I guess you may agree that there are two different waves somehow. The effective wave, which is what is actually propagating in the brain, and then what we pick up at the sensor level, which is particular. There may be a big difference between these two guys, especially in EEG, because it could be just dipoles, could be volume conduction, there could be everything that is happening. So we have to make an inference between what you measure and what's actually happening. So what we did is, okay, can we try to simulate some activities, some models, to try to see whether we can see whether there is a difference in the actual flow of information, the effective wave, and what we see with other methods. So what we did, we basically implemented, I won't enter too much into details, I just want to give you the idea, but I'll try to be as clear as possible. So we implemented basically VAR model, so autoregressive model, where there is the activity X in some layers, in N, let's say 4 regions, there is some activity. The regions are indexed by the I here, this index, and the activity is modulated by some metric. So let me try to make this more clear like this. So you have N layer, and each layer is described by X. So X of 2, for example, is the activity of this guy. And this activity is influenced by itself. So it's autoregressive. So there is some memory, but also by the forward parameter, the A12, and the feedback parameter. So basically, there are 3 parameters that are influencing the activity at each node. This own memory, let's say, the autoregressive part, the forward, and the backward. And we studied 4 cases. So this is formalized basically by these 2x2 metrics, where there is the memory of the first node, for example. Then there is, the second node, A22. Then there is the other 2, A12, which is the forward parameter, the coefficient, and the A21, which is the backward coefficient, basically. So what we did, we studied this model in 4 different conditions, where the autoregressive part is always positive in all the cases. And then we play with the forward and backward sign. So sometimes everything is positive, sometimes feed forward and feedback are negative, or one is positive and one is negative in different conditions. So sometimes this is inhibitory, let's say, where all the other is excitatory, or vice versa. Okay, we tried different implementation with different taus, so with different temporal delays. So either just the previous time step is influencing your activity at the current time step, or with more time steps back in the past. We try both of them with 3 or 7 level. And we also implemented the predictive coding model I showed at the very beginning. We express it as a VAR model, and we test the same idea. So the first thing that we did, we give input to all these models. And if you apply a Granger causality analysis, so what you see here, let me drive you through all the 3 conditions. On the left is the case where there is tau equals 1, so only the previous time step matters. On the right, there is the case where tau is bigger than 1, so more time steps in the past are influencing in the current moment. And this is the predictive coding case. I won't specify the equation, it doesn't really matter. What is important is in all cases, what we see is that there is a bottom-up gradient of information. So the information, according to Granger, is going from nodes 1 to nodes 2. From nodes 2 to nodes 3. So it's basically going forward, which makes sense, right? We are feeding input to our model, so this information, this effective wave is propagating bottom up. But if we look at the phase, and here is when it gets interesting, then the way we look at the phase is take our activity, we apply Hilbert, and we extract the phase, and then we do the difference between nodes. And in case 2 and 3, we see that the difference is around 90 degrees, which means that this is propagating forward, which is in line with the grandeur. But in case 1 and 4, in all the implementation that we tried, predictive coding, temporal delays, without temporal delays, is actually going backward. So the traveling wave, if we would apply a phase-based analysis, we would see a flow of information going top-down, whereas grandeur is actually telling us, look, it's actually going bottom-up. And case 1 and 4 have in common that this parameter is inhibitory, and this is the forward one. So the idea is that if you have inhibitory activity in this very simple linear model, if you have inhibitory activity going bottom up, let's say, then your phases will actually tell you the opposite or what's actually happening in the flow of information. And this is somehow summarized here. So if you have excitatory activity bottom up, whatever is happening on the feedback, then grandeur and the phase will agree. You will see a flow of information going bottom up. But if the forward activity is actually inhibitory, then phase and grandeur will tell you two different stories, which there's not one is correct or one is wrong. They are just different. They are just picking up different things, basically. And so this, to sum it up, this calls for caution in interpreting our EEG data, especially phase-based data. There is this inference step between what's actually happening, what's actually propagating in the brain, and what we actually pick up at the sensor level. So to wrap it up, this is my very last slide. So it's awesome to consider oscillation with their spatial components, so as traveling wave, how they're propagating forward or backward in every direction in the brain. And we saw that forward wave are related to visual stimulation. Backward wave, I didn't show it, but in another study we showed that are related to visual attention, spatial attention. Both of them are modulated by psychedelic drugs in schizophrenia. And we are testing this link, which I found very interesting, between this alpha band traveling wave and predictive coding. So it seems that the story is complicated. It's not as obvious as it seems. So there are positive and negative results, but it's what we are currently basically doing. And lastly, it's important to keep in mind the difference between apparent and effective waves. And there is ongoing work in the team with binocular rivalry, working memory, actually it got published, and computational mechanisms to go more into this understanding of the link between traveling wave and predictive coding. So I'd like to thank all my collaborators, all my amazing collaborators, and my fantastic team. So this is the team which work directly on this project on the ERC. So I'd like to thank, of course, also the funding, the ERC for supporting us so generously, and all the NeuroAI team, and all of you for your attention. Thank you very much.
Andrea, that was wonderful. Thank you.
Thanks.
I have a whole list of questions here myself, but why don't we start with, I'm super interested in your work because it helps, your work with scalp EEG helps explain a lot of the findings that I've been able to see with intracranial.
Right.
It kind of gives a different perspective on things. So I'm really excited about your talk. But why don't we dive in first? Alessandra, you had a bunch of questions. Would you like to dive right in and take the floor? You can turn your camera on and we can have a little conversation here.
Hello. Hi.
Hello.
Hello. Take it away, Alessandra. Yeah.
I do have lots of questions, but I'm happy to narrow them down for time or whatever works. My first question has to do with this like debate on causality between, between different waves. I was asking basically if these map on, if like backward waves and forward waves map on at all to like lower and high frequency bands, and if so, whether you have a take on whether lower frequencies are epiphenomenal. That would be my first question.
Okay, I think I have a slide in which we actually have the sorry, my bad. I actually have it in the schizophrenia case as well, in which we have all the spectra, right? So I think that we have traveling wave in all of them, in all the frequency band. And I focus specifically on alpha. I don't think it's an epiphenomenon. I think it's actually a mechanism of the brain, but this is my guess. So you see, you can have traveling wave pretty much everywhere, right? And of course, a gamma wave on this much traveling from occipital to frontal doesn't make too much sense. I kind of agree that it's. Right. I wouldn't go too far in interpreting this data. But for the alpha wave, I really think that would be my working hypothesis, that this alpha acts as a sort of a director in orchestrating the cortical activity, basically. So it's basically with these ups and downs, is maybe synchronizing gamma locally, right? So some sort of cross-frequency coupling, for example. And so it acts as a sort of high wave in carry the information that I like to think is related to predictive coding, but maybe there's nothing to do with predictive coding, and it's just communication, basically, helping the communication. So I don't think it's an epiphenomenon, or it's just, I think that there might be some phase difference that helps the communication between regions. And sometimes you could switch from a traveling wave to a standing wave, for example, because maybe you don't need to communicate forward or backward, but everybody has to do his job at the same time for some reason, and you could switch between this and that. And maybe there are some nuclei, like maybe the pulvinar or other alpha-related nuclei, that can act in synchronizing the cortical symphony, let's say.
Yeah, that makes sense. You basically answered my second question in your methodological slides. It was basically about how the priors and prediction errors, convey the information signal. So that was very interesting. But related to that, I was just wondering if you would expect with dynamic causal modeling over Granger causality, whether these sorts of information messages would backward or bottom up would become even clearer. Looking at like the actual effective connectivity and, maybe even thinking about the different regions.
Yes.
But the question was mostly about DCM over Granger causality.
Yeah, I think they're all complementary. I think it would be awesome to try all of them, maybe on even better data than EG. EG is great because you can run a lot of experiments very quickly, but it's very limited in the interpretation because there are so many things that could go wrong for volume conduction, dipole, whatever. So actually the work that the Jacob's lab is doing is great because you have data that are much more inside, your intracortical, invasive. Of course, you can do less experiment, but then it would be nice to test all these phase-based Granger dynamical modeling and see whether they agree or not and which story they're telling, because I guess they all make sense methodologically. They are probably picking up on different things, and it would be nice to understand who does what somehow.
Yeah. Thank you very much. I'll let other people ask questions, but I'd love to reach out because I'm working on.
Thank you very much. Thanks.
Daniel Hasigan, I see that you have a question. You want to turn on your screen and want to join the party?
Hey, can you hear me?
Yes. Hey, welcome, Daniel.
Yeah.
Hey, a really cool talk. I really like to see the update on all those projects. Very cool. I'm very curious on if you calculated the speed of those traveling waves using your methodology. If you look at the maximum value after the FFT, and if you can compute the speed across the scalp, and if you can relate that to if there's any frequency gradients between the electrodes and measurement, and then you can relate that to other work with like weakly coupled oscillators. And curious if you've done that.
That's right. Yes. So I'm trying to go to a slide. Let me try to do it properly, because we actually measure in the very first study with Rufan, we had fun trying to compute the speed of the waves. I guess it's this. Yes. Can you still see it? I don't know if I'm sharing. Yes. And so we basically compute the speed of the wave, and it kind of makes sense with what we know from other studies, especially when we consider we smear basically we apply. So we have our model that generates traveling wave. We apply as mirroring as if it was during the EG, and then we see that the speed of propagation actually makes sense with data that are real data somehow. So we were able to match the speed made sense with what we know from other recordings somehow. I don't think that EG. I wouldn't go that much deeper into the interpretation of the speed with EG data. Again, maybe more invasive recording would help to characterize better the speed of this wave. And related to the modeling, that would be great. We didn't do much yet on related. If I got your question right, is to relate this to basically model Kuramoto models or oscillators, synchrony between oscillator, and that would be great. That would be fantastic, actually. There is some work that we did completely different, not on traveling wave, and I would like to link it eventually, in which we have some oscillators in deep neural networks that helps with the phase to do to synchronize for binding by synchrony basically, but we don't see the traveling wave there. It's a bit of a different direction somehow, but it's a very cool, very good question, very interesting direction to explore.
Awesome, thank you.
Thanks.
And Andrea, I have a question for you. A lot of your work on the forward and backward waves was, measured in terms of decibels or power on different kinds of units. But my question for you is if it's possible to interpret. I mean, I'm used to interpreting our data from my lab, where we look at things intracranially, and it's different. But just in terms of like whether there is a forward or backward, like what is the direction on each trial, and then I look at it in terms of percentage of trials that go forward or backward, and I realize it's a very different kind of way of thinking about things, maybe. But I wonder what your take is, and yeah.
Interesting. Yeah, I think it's not so different in the sense that what we do. Well, I'm trying to find the slide. It's basically we do something similar to some extent. I lost it. Sorry, but so the decibel idea is basically comparing with. Sorry, I'm trying to find it, and then I can. Yes. So we have our amount of. This is kind of a probability of traveling wave with respect to the null distribution in which it's shuffled, right? So here you can have a wave or not, basically forward and backward, and then we average these over time. So you can maybe imagine. We can interpret this as a sort of probability, I guess, to some. Well, not really, because it's in decibel, but you can label each trial as having more forward or more backward wave, and once this is done, then we can compute a probability. And actually, to be, I didn't put it here. I should have actually. We are actually analyzing most of our data now also with your method. So we adapt the phase. Fitting, we fit a plane, which is great. Thank you for sharing that. It's very cool. We fit a plane on the EG data, and that's work that Jakob did. We adapt basically and fit the plane, and we have a probability. So we actually see whether it's going. I should have put it here. I'm very sorry. That's a bit sad.
So how do I convert the plots like the ones I'm looking at here? Because the numbers don't add up to. I mean, these numbers here are not probabilities, right?
No, definitely
not. It feels like you're trying to trick me. It feels like probabilities, but they're not, right?
No, they're not. They're definitely not. But what I should have put here is that we reanalyzed so young data with actually it's in the archive of Jakob. It's in this paper. In this paper, he basically did the same thing. We analyzed so young data, and we get very similar results as in decibels. So we have an increase of forward waves during visual stimulation and a decrease of backward, which kind of makes sense. Of course, in this case, it's in probabilities because it does very much something similar to what you did. So each trial, it's either one or the other, or something else if it's not clear based on the fit. And it's very consistent. And that was reassuring because at some point I was thinking maybe the 2D-FFT is actually doing something that doesn't make too much sense. But no, they kind of agree, which is reassuring indeed.
Cool. Irfan, did you have a question?
You almost covered my question, but maybe
come on, we were asking the same question.
But maybe a quick follow-up is, it's more related about the situations that you have similar probability of forward and backward waves. Maybe that's a measurement, and maybe it's related to how we measure them, or maybe that's something that sometimes we need these back and forth super fast type of waves. Do you think you can test it with some tasks that you don't need predictive coding, like some novel stimuli that you really don't need that forward backward interaction, or changing the task to see if you lose those kind of near 50% level of forward backward waves?
Right. That's a good question. So what we see with the phase fitting, for example, is that most of the fit are still forward and backward for alpha, especially for alpha. So that's the main direction. I agree that the predictive coding framework is fun, it's nice, but it's an interpretation. So it's something on top. So maybe it doesn't make sense. Maybe it does to some extent, and that's all good. I mean, that's the funny part, is to try to figure out how much it makes sense somehow. But the directionality forward and backward, at least for alpha, I think it's the main, at least with the EEG, of course. So what we pick with the EEG is this. Maybe with intracortical or in non-human primates or in mice, we can see better other things that we wouldn't be able to see with the EEG. It's either direction or more precise, spatially resolute traveling wave.
Yeah, nice.
Makes
you.
sense. I don't know if I understood if I
No,
understood
yeah,
correctly the question. Yeah.
that makes sense. Yeah, the fact that you said the predictive coding is one interpretation of that.
Sure. Yeah, of course. But I like it very much personally, but
Yeah.
I'm well aware that it's, I mean, one way of looking at things, but it could make no sense. There are many other ways, and of course. Yeah.
Thank you.
Thank you.
I think we'll take one last question from Andrew Pale.
Hello.
Hi, Andrew.
Hi.
Yeah, Devin.
Question coherent? Is that a reasonable concern? The source localization problem confounding the ability to determine the direction of the traveling wave to some precision?
Yes, that's an excellent question. There is some work that was done by Rufan and the previous postdoc, actually, in which they tried to source localize with the ECOs, which was a specific paradigm actually with the flicker, and they found a bit mixed results, not very convincing, not very conclusive. There is the work of Zigalov and Ole Jensen, in which they also found the source localize. I think it was again with perceptual echoes, so it's a cross correlation with the stimuli, so it's not really alpha, and they found basically 2 dipoles would be enough to explain most of the pattern of oscillation. My way to go would be to use less DG and maybe use different techniques. Now I'm getting more into the MEG, for example, MEG, who has less problem and it's easier to localize things, for example. So if I would rely more on that rather than dig too much with the data that I have with the EG, I would rather change approach, MEG, I trust it better and probably would be more reliable. But I totally agree that's a very relevant question, very important, and we shouldn't go too far in the interpretation of the results in terms of localization.
Okay, thank you. I think we will wrap up now. Andrea, that was wonderful. I have some more
Thank you so
questions
much.
myself, which I might send you a note about.
Sure, with pleasure.
But I really enjoyed it.
Thanks again for organizing. It's really, really great, and I appreciate a lot. Thank you so much.
You're welcome. This is just fun for me, so I enjoy it. Okay, I think we'll wrap up. Bart, Irfan, Uma, did I miss anything?
No, this is great. Thank you.
Okay. All right. We'll see everybody in about a month. Keep an eye on our Twitter and Blue Sky feeds for more information. Andrea, again, thanks for the great talk.
Thank you.
Have a good evening to you. It's dinner time for you, I would imagine.
Yes.
Yeah. Thanks for staying late for us.
Cool.
Okay.
Thank
Take
you.
care,
Thank you very
everybody
much.
else. Cheers.
Bye. Thank you.